Hello, beautiful humans of the internet. Actually, hello to humans, cyborgs, robots, and of course, eventually, when this signal reaches you, hello, extraterrestrials. Greetings and salutations from planet Asturias, here in lovely northern Spain from La Pipa. I am here with my trusty and faithful robotic cyborg plushy colleague, Gopherbot, and we are here to have a little fun hacking. So I'm going to take off my protective coverings because fortunately for me, Gopherbot has now had the vaccine. So congratulations. Obviously you are an essential worker and I am not. All right, so we've got some fun things to do today, hopefully, including maybe a little surgery on Gopherbot, but we'll get to that. So it's been a very busy week for all of us in Internetlandia. I'm sure you've all been doing lots of cool stuff with technology and code, and of course with Go. So we've been getting a lot of contributions coming in from our amazing community with the announcement and release of TinyGo 0.17 a couple of weeks ago, here live from the Pipa while streaming. So our contributors are out there 24 hours a day on this planet. I'm not sure how many hours on whatever other planet you might be listening to this from, but all of them, trust me, all of them. So actually, we do have an interesting, how would I say, packing or clustering of TinyGo people who are here in Europe. There was a very cool map that was created. Let me see if I can find it. That was, who actually created it? One of our contributors. So made a map which, although not comprehensive, will hopefully show a little bit, and I think it was called Starcast, Starwatch. It's somewhere in my history. But they made a map that showed all of the GitHub stars and where they were coming from. And then somebody else did a map that was all of people signing up on your own of saying where you were located, like putting a pin in it. So let's see if we can find that one. It's on a service, I think, called Ethermap. And if we take a look at that, you can see that there is definitely these are self-reported, not the same as the GitHub stars, which basically showed everybody who'd ever started. These are people who entered it on their own. And you can see that there's definitely a clustering here in the free countries of the European Union, where I am a resident. But also, if we looked at the other map, which I can't remember where the link is, I'm sorry. If somebody knows where that is and you can paste it into the stream, then I would be most appreciative, into the chat comments on Twitch. It's called like Starcast or Dreamcast. It's a GitHub repo that probably ran out of Google Map credits. Anyway, so we've had a lot of great contributions coming in, and now that the new release is out in the wild, we can hopefully get to some of them. One in particular that I was looking at that I thought this really needs to get merged is a contribution from team member and very active contributor Takahago-san, Sago35 in Japan. So we have a pull request for the SAM D21, where is this here, to improve the SPI interface. So what is the SAM D21? So that happens to be the board that is used in many different pieces of, or the chip, I should say, used in many different boards. This one is the Arduino Nano 33 IoT. And if you were one of the fortunate people who were together with us in real life at the last physical real world GopherCon in San Diego, then you probably got to take one of these home. This is a really cool board from Arduino that uses the microchip ATSAM D21 microcontroller. It also happens to have an ESP32 compatible Wi-Fi chip on board as a coprocessor. But so this chip is got a SPI interface, which, as you maybe remember from the last time, the SPI interface is the interface that is used for the serial peripheral interface, and we use that for lots of different kinds of devices like screens, sensors, some LEDs. I'm having luck switching back from my, may have done something wrong to my controller. I'm not having luck switching back from my other camera view. Oh, here we go. I was just too impatient. I pushed the button too many times in a row, now it's going to switch back and forth. You ever seen that happen? Well, you're going to see it now, my friends. You'll see it now. That's the side view. Hello. All right. So where were we? Oh, yes. Hopefully we will eventually get back to my Linux desktop, where I have this great pull request from Sago35. So you may have seen one of his previous pull requests, which are probably the most amazing pull requests I have ever seen, especially with these peripheral style pull requests, where the serial peripheral interface, if you recall, is the interface that we use to communicate with different screens and sensors that generally require a higher speed. And so the way it works is it has two lines. One is the data out, and the other is the data in. And using these two lines, by pulsing on and off at a frequency rapid enough, we can send the zeros and the ones, which are a binary signal. All right? So the previous implementation of the SPI interface had basically some type of error in that it was adding a nearly half, over 500 nanoseconds worth of delay, which is, in terms of the high-speed communication that we're talking about here, that is just an unacceptable delay. It's really, really serious. So he went in and figured out how to get rid of that delay by using, similarly to, I think, the implementation that we saw in his last pull request for improving SPI support, basically by using a buffer to store the data and then separately sending it as fast as the port can take it. We are able to make it so that the processor always has work to do and is not waiting for this serial port to finish, either sending or receiving the data, depending on which direction it's going. Now, one thing that's interesting about the SPI interface is it always is a full duplex interface, which means it's always both sending and receiving at the same time. So whenever we send a byte, we're also receiving a byte. If the device that we're using does not actually send data, if we're just like it's a screen and we're only writing to it and it doesn't send any data back, then we just throw that by the way and ignore it. So we can see here from the output of his signal analyzer that the previous implementation had this very long delay in between the individual bytes that were being sent, whereas his new implementation is substantially better. You can see there aren't the gaps in between the different signals being sent, and same thing with receiving. So the only reason I didn't merge this already is because we need to test it somehow. And I thought, what a great way to test it that we could use our Arduino Nano 33 board, and I could use, additionally to that, one of my favorite SPI devices, which is the APA 102 LEDs, also known as NeoPixels. So NeoPixels is the brand name when it's sold by, I got to turn the light on here. So I think there's a light. You might be able to see a little better. Maybe it's not plugged in. It's not plugged in. Of course. Well, good enough for now. Excuse me. So the NeoPixel strip here, each one of these LEDs, let's see if we can get a little better focus. while also not getting rid of the light. So each one of these LEDs is actually a separate integrated circuit. We have a light, but it's just not plugged in. So if we plug it in, oh, that's great. I have a lighting operator now. The crew of this production is getting bigger and bigger. So you can actually see each one of these LEDs is a separate integrated circuit. And when you communicate by sending in the signal through the SPI interface, what happens is it actually relays the signal to each one of the APA 102 LEDs in the strip. So you can imagine this is something called daisy chaining, referring to the lost art of creating flower chains, which is actually a very, very soothing thing to do. I highly recommend it in the springtime. So each one of these has to relay the signal along to the next LED, so you can see where performance and speed would be very important if it's able to keep up, right? So I'm going to use the Arduino Nano 33 and this APA 102 just to make sure that, in fact, it's working. I'm not going to try to analyze to see if the speed is actually faster or not. I really feel pretty confident from the work that Saga35 has done with his signal analyzer that, in fact, yes, it is faster. I just want to make sure it actually still works. That's always a good idea. So let's go and merge, not merge, but let's just pull from the command line. So because I don't have to want to remember things, I will just click on the command line instructions. Of course, I will have to change these command line instructions a little bit because I don't like them, but for now this will work. So I'm going to copy just the name of the branch. And so let's go over to my terminal window here where I've got my TinyGo dev branch in here. So let's git pull rebase origin dev is how I pull down the latest changes from the development branch on GitHub and then bring those into my current working branch but without a merge commit. Hence git pull with the -- rebase. So we'll pull in the latest dev branch just to make sure we pick up all the latest commits, which something earlier today. A few commits that made it in. Some housekeeping commits to clean up a few extra smoke test files that were left behind on the CI. A few commits from Ike, project founder and our most prolific contributor by far, to improve the compiler itself. Some improvements for the STM32. All right, so we need all that. So now I'm going to git fetch. And so that's going to pull in all the names of all the different branches, including the one that was added with this SAM D21 SPI branch. So if I check out a new -B, meaning create a new branch, named SAM D21-SPI from origin, so now I am in that branch, right? So this is that second command. So GitHub tells you git merge dev, meaning take the latest commits from the dev branch and bring those into this working branch. But I don't like to have a merge commit. So I instead will go git rebase dev. Git rebase dev does essentially the same thing, but it does not create a merge commit. All right. So I'm going to run make. Just probably don't need to, but I'll do it anyway. These changes are only to TinyGo's machine package. They don't actually change the compiler itself. But because there were a couple of changes made to the compiler since earlier today that I haven't picked up, so the make task will build the TinyGo compiler from sources locally on my machine using the local version of the LLVM toolchain. So LLVM is a framework for writing compilers. If you've seen any of my talks at FOSDEM, for example, I went into a bit more detail about how awesome LLVM is. We are big fans. We could not exist without LLVM. Also, we contribute to LLVM the best we can. So, all right, so now it's done. So we'll copy our completed binary, and let's run TinyGo version just to make sure that we actually picked up the correct version. And so yes, it is the 0.18 dev version, showing the SHA of our most recent commit, which is FD6, just to make sure we got the right one. And yes, it is FD6. Okay, we're good. All right, so what was this test we were going to do? So we're just going to try to see if Sago 35's changes to improve the SPI support on the Nano 33 actually work, or if they break it. So I will assume that this is going to increase the speed, as he says in his analysis of the pull request, but I'm just trying to make sure it actually still works by sending some signals to this LED. So if I go over to our drivers repo, which is where I have, so I use GVM to switch versions of Go. GVM is the Go version manager. And I use this because I generally need to switch back and forth between, 2 to 3 different versions of Go at any given point in time just to do testing, make sure things are still working. So, and then we'll go over to the TinyGo repo that I have with the drivers in it. And we'll check out the development branch, since I was testing some other things in there before, as you can see from the branch name here. I have my bash terminal set up to tell me which Git branch I'm in, so because I tend to forget, like we all do. So let's check out dev, the development branch. We call our development branch dev, and we call our latest release branch release. It's hopefully a little easier to remember that way. Probably still hard, but All right, so let's git pull rebase origin dev. Same thing we did on the main TinyGo repo. We're just pulling in any changes, which there haven't been any since I last pulled. So the reason why I had to do this was because I needed to check to see the example that's in the TinyGo drivers repo for the APA, where is it here? The APA 102 NeoPixel LEDs. So if we take a look at the example I have here, it's set up to work with a 30 LED strip, and as you can tell, I don't actually have 30 LEDs here. Get the focus a little better. I only have 6. 1, 2, 3, 4, 5, 6. So, as you might guess, that probably wouldn't work too well. It may not even work at all, because the way that the NeoPixels work, it has to relay this signal along from the first LED to the last LED in the chain before sending the next signal to the first one. And so if there's only, if there weren't the same number in there as we actually claim, then that would be a bit of a problem, wouldn't it? So I'm going to go back in here, and I'm going to change the count of the number of LEDs to 6. That way, this should work. And I'm just going to use the normal SPI 0 interface, right? Because SPI 0 is something important to mention about the Arduino Nano 33, which I know I did mention earlier, it does have a built-in Wi-Fi chip. And that Wi-Fi chip, it's an ESP32 separate microcontroller. So that Wi-Fi chip is connected both by a serial interface, a UART, and through a SPI interface to the main microcontroller, the SAM D21. The reason for that is that the SPI interface is a lot faster, and if you want to send a large amount of data to the Wi-Fi, you're probably going to want to do that, right? Now, luckily, SPI 1 is, I believe, set up to talk to this chip, and SPI 0 is available for, whatever else we need. So you might notice there's no pin numbers on the top of this board. So the reason for that is the board has so many components on it that are so tightly packed together that there just wasn't any room to silkscreen on the top of the board anything that would actually be large enough to be legible. So in order to get around that, the solution was, put the silkscreen on the bottom side of the board. The problem with that is that's the side of the board that you plug in to the breadboard. So in other words, you can't see the numbers while it's plugged in. Luckily, my colleague, Justin, awesome programmer and amazing human being in Los Angeles. Hey, Justin, miss you, man. So he did this, thankless but incredibly important task of taking a picture of the Arduino Nano 33 and putting the numbers on it. And that way we can look at this and we can figure out which pins actually match our SPI pins. So one way we can tell that is in the machine package documentation for TinyGo, which is on the website. Whoops, if I would not close it. So we have here information about the different pins, and you can see that our SPI pins for our normal SPI interface, where are they? They're in here somewhere. That's UART1, SPI 0. SPI 1 is the one that's connected to the Wi-Fi chip. That's what we were discussing. So if I just use the default pins for SPI 0, then that should work. Okay. And I've changed my code to use only 6 LEDs instead of the 30. And so what this program is going to do, let's just take a look at it real quick. It's going to open up the SPI port. It's going to create a new APA 102 LED strip with 6 LEDs, and then forever it's going to loop through and it's going to alternate the colors of those LEDs, switching between red and green, and then sleep for 100 milliseconds. So 10 times a second it's going to cycle through this red and green kind of, Christmassy looking color. All right. So let's go back to our terminal, and if we TinyGo flash, where our target is an Arduino Nano 33, and the program that we're going to flash is from our examples, and it's the APA 102. Now we do need to plug in a cable, so let's plug in the cable from my computer into the Arduino's USB port. So the Arduino Nano 33 uses a bootloader that's known as the BOSAC bootloader, which is actually provided, I believe, by Microchip directly, as opposed to the UF2 bootloader that I've generally been showing from the different Adafruit devices. So, so this bootloader, we also actually need to plug in the cables for the board to the LED strip, right? And we have 4 cables here. We have power, we have ground. Actually, wait, let's look a little closer here. Ground is black, power is red. Very commonly, you'll see that the ground is black and the power is red. It's not written down. It's not like an official rule. It's more like a custom. Something that's generally polite to do, like opening the door for somebody else and letting them walk through first. This is like not causing their electronics to blow up and let out the magic smoke by putting the same colors of the cables. And then we have these other 2 cables here. Let's see if we can see. You might be able to see the writing on here if we get close enough. You can see on here let me focus it. There we go. So you can see that there is ground, G and D. You can see that we have at the bottom, the red one, 5 volt, 5V. And then we have DI for data in. And then we have CI for clock in, right? That way the data and the clock, there is no output from these LEDs, there's only input. So I'm pretty confident that we can plug the ground into the ground, which on this board all of the little spots on the top that have that white marking on the background are the ground. It's usually good to plug the ground in first. Okay, so slip in the ground carefully into this hole, hopefully. Not bending it too much, all right, so that's good. All right, so let's go back to our diagram here so we can figure out actually which pins go in the other places. So we go back to our picture, and so we need to know which one of these pins matches the clock in, and which one matches the data in, and of course which one matches the power. So in TinyGo, under the source machine is where all of the board definitions are. And if we go to the board for the Arduino Nano 33, that's where it's showing us all of our pin mappings. And you can see this is the same information that was being displayed on the TinyGo website. We actually extract this information from the files automatically, and then we repost it there to make it a little easier to see. All right, so if we look and we see our SPI pins, our SPI clock pin is D13. So D13 is the pin that's all the way on the end next to the USB port. And you'll see that the 3.3 volt is right next to it. Now, didn't that LED strip say something about 5 volt? And this board says 3.3 volt? Dead program, are you sure that's a good idea? Well, generally speaking, you don't want to do these sort of things. And if you're going to use a large number, say more than 6 of these NeoPixel LEDs, you probably are going to want to power the LED strip with 5 volts. But you don't want to plug 5 volts into a board like the Nano 33 that can only take 3.3 volts, or you will let out the magic smoke. You don't want to do that. So you would need to have some type of power converter so that you can convert the signals from the Arduino Nano up to 5 volts and only power the power strip with 5 volts. So that's a little more complicated. If we're doing it only with a small number of LEDs, we can get away with it. All right. So we see that pin D13 is where we want to plug in to get the clock, right? D13 is the clock. And then the 3.3 volts is right next to it. All right, so let's go back here. And we see that our clock pin is the yellow one. So that should go over here. Remember that the diagram is kind of reversed relative to the... There we go. That way the image is going the same direction as the diagram is. Make your life a little easier, and mine, of course. All right, so what we were saying, yes, so the clock pin, which is, what color is clock? Yes, yellow. So the clock pin goes at this far pin over here on the end. And then the power is the one that's right next to that. And that will just mean only the data will be left to plug in. So where does the data go? So the data goes into pin D11. Where is pin D11? Pin D11, of course, is on the other side of the board, and it's one over from the back. Yes, this is obviously very easy to make a mistake. So other side of the board and one over. That would make it this one. And then we'll plug in the power, which is the one next to the clock. And of course nothing happened yet because we didn't actually put the program on, right? We haven't flashed the code. So let's go over to our terminal window where we were before. And so we're going to use the TinyGo flash command. TinyGo flash -target Arduino Nano 33. Just a little delay in switching my camera view here. For some reason. Too much streaming, not enough time to respond to those commands. So we'll just flash it. And if it works, then yes. It's kind of hard to see because it's so bright. We have so much light. The power of the Force. This is the way, my friends. This is the way. You can see that, wow, it looks almost extraterrestrial. Yeah. So here this angle you can kind of see a little better that it actually is, in fact, lighting up. Now, finally, it switched back to the other view. You can see here it's lighting up each of the LEDs, and the fact is that it's actually working means that this code is acceptable to be merged because the speed is increased, as we saw on the diagram from Sago 35, and it didn't break the existing functionality that we have for this LED. So awesome. Thank you very much for another cool contribution. So let's go and merge that in. This is the highly glamorous work that is necessary for maintaining an open source project. And it's so cool. I love it when I wake up in the morning and there's a bunch of pull requests from people all over the world adding cool features to the software that we can all use. I just think that's amazing. So let's take a look. It has 2 commits. Let's see what these are. All right, so the first one improves the SPI interface. What's the second one here? Add special handling when SPI frequency is 24 megahertz. So it looks like it was kind of an important change. So I'm going to go ahead and merge these as 2 separate commits instead of squashing them together, because that seems like it's, something important enough to actually leave as 2 separate commits. So thank you very much. Thank you very much. You should always thank your contributors. Please and thank you, very important words in whatever language you say them. And we are now merging. And it's merging it into the dev branch. And when I say merge, I actually mean rebase. So in GitHub, you have 3 options. One is create a merge commit. That's probably the worst option. It commits all of the commits from the branch in question, plus an extra commit to say that it's been merged. Squash and merge takes all the commits and turns them into a single commit. That's very good to use when, for example, it takes me like 25 commits to make one simple change, and I would like to make it so people don't have to go through that same pain every time they read the commit log, so I'll squash them all together. And then the one that I'm actually going to do this time, which is rebase and merge, which is just take these 2 commits and bring them into the dev branch. So we'll rebase and merge. We'll confirm. Deleting the branch when we're done to clean up after ourselves. And thank you very much. That was awesome. Cool. All right, so that's the contribution for the week. We have a lot more contributions. Actually, as Sago 35 himself pointed out to me, we actually have quite a few contributions that need very badly to be reviewed in our drivers repo. Sorry about that. I need to get to those commits or those pull requests, review them, give any feedback, and or merge them in. So I'll make sure I get on that very soon, because we really do appreciate this work that everyone's been doing, and we'll try to bring it all in some type of coherent way. So sometimes we don't merge a pull request right away, like usually. We definitely look it over carefully, not just, it's not just because we want to, dot all the I's, cross all the T's just for the sake of doing so. No, it's really not about that, at least not for our team of collaborators. For us, it's more a matter of, over the long lifespan of a project, if you have something that you can do to reduce the amount of friction it takes both for a new person to add some code and for you as a long-term contributor to be able to review the code, if you have some coding standards if you have some basic principles that you try to stick by, it makes it a lot easier both to explain what these ground rules of play are to people who want to contribute, and it also makes it easier for you when you're looking at some code to go, oh, this code is, maybe it's older and we changed what our standards are, so it's a good thing for us to maybe refactor. Or, this code is perfectly fits exactly what the way we like code to be formatted, not just formatted because Go will format it for you, but structured maybe is a better way to say it. And if somebody else also wants to add some functionality, they'll be able to figure out where to add it into. So that's really the reason behind it. So I will get back to the drivers real soon now, I promise. Sorry about the delays. But so many contributions. You're all so awesome out there. All right. So one of the things that I wanted to get to, but that I didn't have a chance to, was Gopherbot. So if Gopherbot was, or is, I should say, a toy program with TinyGo made from the robotic gopher, or made from the gopher plushie, which is the official mascot of the Go programming language, created by the brilliant and equally humorous Renee French. So Renee's influenced a lot of gophers of all different kinds by all sorts of artists. And my brother Damon is one of them. He is the one who actually did the 3D design for the Gopherbot helmet, and I did the electronics and the programming. So Gopherbot is using a board that is known as the Circuit Playground Express. Maybe we can get a little better view of it over here. So the Circuit Playground Express is a very cool board from Adafruit that is very unique in its circular form factor. It's got a bunch of NeoPixel LEDs. You can't even see them because the other ones are so bright. Actually, it's kind of a cool, disco effect. So these same kind of LEDs that are on the strip are also on the backpack for Gopherbot. And we can see that when we plug in Gopherbot. Same LEDs. Got to plug it in. Or are they? Guess what? I lied. They are RGB LEDs, but they're not NeoPixels. So they are, in fact, a different kind of LED that's known as the WS2812. So that uses a different interface than the SPI interface that you saw on those LEDs I showed on the strip. That interface uses both a wire for the clock, a wire for the power, a wire for the data, and one for the ground, so 4 wires. This one only uses 3 wires for all these, and so, as you may guess from looking at the size of this board, space is kind of at a premium, right? So, anyway, this was the board that we used, the Circuit Playground Express, for Gopherbot. There was a crowdfunding campaign. Thank you very much for everyone who contributed. We really appreciate it. So there's a new Circuit Playground Express, a new Circuit Playground. It's the Circuit Playground Bluefruit. You might remember this from my FOSDEM talk earlier this year, Go Without Wires. So it looks really, really similar. In fact, this is a great time to pull out, everyone's got a new board, to replace their old board. Just because you can't, have the same board 2 years in a row. Well, no, you can, actually. But, it's great to have new boards with new features because new chips come out with new possibilities. So, for example, the original BBC Microbit and the new BBC Microbit V2, right? Pretty similar, same basic form factor, kind of similar idea, same flavor. So Adafruit doing a very similar idea of keeping the same sort of form factor, and now that's, a round, cool flying saucer type board. But similarly to the BBC Microbit, this new Adafruit board is substantially more powerful. It has a several other peripherals on board, like a speaker. Um, Actually, this also has a speaker, but it's a better speaker. And most importantly, it has a microcontroller that has Bluetooth. So, Gopherbot, what do you think about brain surgery? Gopherbot is willing. Gopherbot, being a robot, will do whatever commands we send. In this case, we're just going to do it manually. All right, I see. The reason why this is such a weird angle is because we had a small accident in the studio before. Luckily, no one was hurt. I'll try not to do that again, I promise. All right, so Gopherbot here, we're going to try to perform a certain... Oh, the light is so much better here. It's good enough. Yeah, we could see. Actually, maybe I'll do the surgery under the micro camera. That's usually a good idea. Last time I got a surgery, the doctor used a microscope. Does that mean... What does that mean? It means I assume that they were very careful. All right, so let's switch back to the micro camera here. Eventually it'll pop back over. So in the meantime, I'm going to do a little bit of disassembly. So I'm going to unscrew. So keep in mind that these cables must go back to the same places. I'll just do it manually. So let's unscrew first the screws that are holding in the power. Okay, so we'll take off these 4 from the backpack. We will remove the harness. Okay. This is a serious part of the surgery now. Okay, so let's actually take the backpack off. So the backpack is also 3D printed, and it uses these screws to hold the board on, along with some washers as separators. So you can kind of see in there, it's a little tricky. So let's unscrew these. And I'll put them down here so I don't lose them. And let's take this one off. There's 6 of them, as you can see. The other screws that are in there are only to hold the cables on. They don't have any other purpose. And so, as you might guess, they conduct electricity. So we have to use conductive screws of some sort, generally aluminum. It's very common. Steel. You never see copper screws unless it's some electronics that is very, very sensitive, because it doesn't really have to do much except hold the terminal onto the actual conductor on the board, which is copper. So that generally conducts quite well, as long as you tighten it down enough. So we've removed 6. We're way past the first incision, Doctor. We're way past the first incision. If I destroy Gopherbot, you know how mad Salvador, my son, is going to be? This is the one that he made. I always bring it just because it's got a cool black helmet. I mean, black and pink, what's not to love, right? Awesome colors. I have a purple one, too. That one's also very nice. That's actually my favorite color. All right, so we got all the screws off. So if I lift it up carefully, no, they're too tight. So I'm going to have to actually push them through. Or I might even have to actually screw them, because they might be so tightly in there, they might have sort of tap themselves, meaning create their own little screw hole with a thread. So I'll just give them a little turn, because that's probably enough. Because I do have to remove these screws to replace them and put them on the other board. Okay, so There's one of the longer screws. There's one of the longer screws. This is the first brain surgery I've done on a gopher. We're just full of firsts here. This one's a little tight. Probably need to give it another turn. Try to get it loose. So one of the reasons that... Oh, thank you. Yes, we need water. It's good to remain hydrated. All right, so one of the reasons I'm doing this, it's not just new to be new. I mean, of course it's new to be new. But I have an actual reason, besides just the Bluetooth. So there is a very cool framework for doing machine learning on microcontrollers. It's called TensorFlow Lite for microcontrollers. And as you might suspect, it comes from Google. Along with the main TensorFlow is a sort of miniaturized version whose purpose is to be able to execute on highly constrained hardware, like embedded Linux devices or on microcontrollers. So the 32-bit ARM microcontrollers, such as the one that is on this board, is one of the supported platforms. So in the very near future, I plan on doing some work to see if I can make Gopherbot artificially intelligent. Yes, Gopherbot will learn. First thing Gopherbot will probably learn is don't let me perform brain surgery on it. But never mind that. I feel like there is a small washer about to fall in my hands. There is. All right, we almost got this completely disassembled. So if you were one of the fortunate people who took part in the crowdfunding, you got a kit. We provided Gopherbot in kit form. I didn't realize, for some reason I thought people would like me to put them together for them. That was so untrue. No, of course, people wanted a kit. Naturally, a kit was much harder to produce than just a fully assembled toy, because you had to also provide instructions. Okay, so now the brain has been removed from the brain case. What could go wrong? All right, so we still have a few screws to take off here. These, specifically the ones here on A2 and A3, which are the two pins that we use to control the LEDs on the NeoPixels that are on the outside of the Circuit Playground and the Circuit Playground Blue Fruit. Okay, now we have a spare board. And here is the new brain. This board belongs to Gopherbot. All right, so we need to put this on correctly. And the easiest way to do that is probably going to be just put in the longer screws first. And then once we put in the long screws, then we can deal with the short ones, because they will take a little bit more of a special touch. I'm not going to screw them all in. I'm just going to put in enough so that we can connect the wires and make sure that Gopherbot will be able to come back to life. Because if not, Salvador is going to be really mad. All right, let's see if we can get this on here. There we go. So there's one. Remember, the long screws go through these longer standoffs, and the short ones are intended just to go into these little short holes. Now, it's a little tricky to get the short ones on, but we'll do this. I'll do it in the same order, because that's the simplest to explain. Also, I forgot my hemostats. So we won't be doing it that way, will we? I only actually need 3 screws on this side to hold it together, and then the other 2 for the wires. And that will be really quite sufficient for... I mean, if you left the hospital and they're like, okay, we only reattached one of your legs, but, the other one will be fine. You could do that at home. Actually, that is what they do in the U.S., isn't it? Well, anyway. Here we are. Okay, we got those three. And let's put in the two shorties. If we can fit them in there, hopefully. It's a little tricky, but we can do it. So you see I have to like slip it in the side. Push it in so it's just correctly aligned. And sort of drop down the screw. If I drop it down properly, it'll sort of find its way in. It didn't work that time. There we go. We don't have to get it tight right this second. We just got to make it so it doesn't fall out. So we'll just rest the brain on the patient. You ever wonder if surgeons do that? Like they just like rest their coffee on your abdomen while they're doing the surgery because they're in there for a really long time. And they're like, hey, what happened to that Starbucks? What Starbucks? I don't know. Some 20 years later on the sonogram, they're like, you have a plastic lid inside of you, sir. Like, that's impossible. I'm not made of plastic. I probably should have screwed this on first. I think that is how I did it last time. Yeah, because we do need this screw. Otherwise, it won't work. Yeah, I need another tool. Luckily, I have another tool. I have my handy dandy Leatherman. This is a very cool Leatherman that Intel gave me back in the day. And this is the tool that I used to have a lot of these. And they've all been confiscated at different airport security places in the world. Because you look at this tool and you instantly know that this guy is going to be able to reassemble the airplane while in flight using nothing more than this very small Leatherman. I have to say this is usually my tool of last resort, not first. You can see why. Barely fits in there. We're going to do it. It's going to happen. It's a little stripped. Well, actually, here, the easiest way to do this is going to be take it off and put it in again. This is the equivalent of undo in physical computing. That and the solder sucker, known more officially as a desoldering bulb. I have to say, those are two of the tools that have really changed my life. Wait, I could take solder off, not just keep putting it on forever? It's not... Oh, wait, I think I got it. I think I got it. I think I got it. Okay. All right, let's do the next one. We need another shorty. Because we need these two in place, or else we're not going to be able to put the two terminals on there, and we will not be able to see the LED visor and the blinky LED on a spring. Those are really important. You have no idea how much time I spent on the LED on a spring. In fact, if you Google Boingy LED, you'll probably find nothing but references about Gopherbot. It's probably the most patentable thing I've ever done, although I work in open source, so I think patents are bad generally. But I might have to make an exemption for the springy LED, because, you know, that was one of the better ideas. Okay, so now we've got enough in there that we can do what we originally planned. Let's put the backpack on in order to do this part of the operation. And so put the first terminal. Actually, let's do the second terminal first. So we have to slip this in. It's a little tight. Need to loosen it. I know, I just tightened it, now I got to loosen it. It's not such a good idea. Okay. Oh, it's because I want to put them on the bottom. All right, we got the first one. So we'll just tighten it down. Okay, now let's do the second. Got to loosen it a little bit, just slip it in there. It has to be tight enough to have a good connection. All right, there we go. We got the second one on there. So let's screw that on. Now, the power. This one we do have to loosen it a bit. Okay. Let's tighten that down. And then the ground. We probably should have connected the ground first. Didn't I tell you that in the beginning? But it's not actually powered up yet, so we should be okay. Right. If there was some lingering capacitance, meaning a little bit of electric charge, that's the reason why they give you all that packaging with all those warnings that say, you know, electrostatic discharge may cause your very expensive phone to basically stop working forever without even letting out the magic smoke, just quietly dying. That's because of electrostatic generally and CMOS electronics. All right, we've got everything screwed in, not all the other screws. So now if we plug Gopherbot in, I don't think I have any actual, oh, there's something on there. You saw it flash. All right, so let's take a look at some code real fast. So I started playing around with Gopherbot 2.0. I don't know if it's actually Gopherbot 2.0. Maybe it's just Gopherbot Next, Gopherbot Bluetooth Edition, Gopherbot Unchained, Gopherbot without wires. One of those. I don't know. Anyway, I made a few changes earlier in order to see if Gopherbot's speaker would work. And so I added a make task demo BLE. So I like to create make tasks for things that I might very likely forget how to do, which, for example, how to flash this board. So, nope, it won't work because I have not converted all. Oh, yes, we recently changed our analog to digital converter interface so that now it uses, instead of just a simple configure with no parameters, now it requires you to pass in some kind of parameter, which is the configuration struct. So I believe I should be able to say machine.adcconfig. And it's just this plain struct. I believe that's it. But actually it was not on the accelerometer, it was on the thermistor, which is the temperature sensor. That's probably why it... oh, and it was not actually, if we go back to the actual error message, we'll see that the problem is actually in the drivers themselves, that the thermistor driver has not been modified. Ah, okay. Because this is using the older version of the drivers and not the newer release. So if I say go get -u for update, and we say tinygo.org/x/drivers, this should update the package to, yes, version 0.15.1. And so now if I try and run it, it has a different problem. So sensors 56. So sensors line 56. That is where we did I had the right idea. We do need to pass in the machine ADC config struct. This is here just for future proofing in case we end up with an analog to digital converter that takes some special parameters. And now it is flashing it. And if we go to the main camera, if I carefully extract the patient from the surgical chamber, you'll see that Gopherbot's lights are on. The Cylon eyes still work. And the backpack cycling. This is the accelerometer. That still works. Oh, listen. Yes, the audio worked for the speaker when it complains and it gets knocked over. So yeah, it looks like so far so good. It was a successful transplant. Gopherbot still does all the Gopherbot things that Gopherbot ever did, just now with a whole new brain and with Bluetooth. And in a future episode, we will go further and we will actually put some intelligence inside that. It's going to take a little bit more preparation, maybe 2 episodes, I don't know. But we're definitely going to do it because it's just too cool. All right. I've been wanting to do that for a while. In fact, I've been wanting to do that since we got the Bluetooth support started. Like, I totally want to program Gopherbot with Bluetooth, where I can, use my phone from across the room to make Gopherbot, do funny things with lights or whatever, or possibly implement the Bluetooth audio interfaces so that Gopherbot's lights can pulse with the music. Actually, Gopherbot's lights can sort of do that now, because the microphone that's built in, you can write a program that just detects the sound levels. But that's not what I'm talking about. I'm talking about like a really cool, not just a VU meter, but like a frequency analyzer, something like that. Something that's obviously overkill for a toy, or is it? Remember, every sufficiently advanced technology starts out in the form of a toy. Very important. Keep that in mind. All right. So I brought some other toys, speaking of which. So a bunch of you may know that the new Raspberry Pi Pico microcontroller came out fairly recently. So if you are not familiar with the name Raspberry Pi, then you've definitely been living on a different planet than the rest of us. It's a very, very cool series of small form factor computers that are just on a single board, right? Just one board. And so Raspberry Pi decided they were going to go even smaller because the Raspberry Pi Nano, I believe it is called, they have a Zero, there we go. The Raspberry Pi Zero is really small, right? But it's not small enough. Also, it is a single board Linux computer, so it has the power requirements of a single board Linux computer as well. This, on the other hand, the Raspberry Pi Pico, is a microcontroller. So it's the first microcontroller from the Raspberry Pi organization, and so it has a lot of similarities to the form factor of the Raspberry Pi. So the idea here is, if you have a Raspberry Pi and you wanted to do analog input, which is to say you wanted to receive data from a thermometer or from a rotary dial or from any of the different analog style devices that exist in the world, you would need to buy a separate microcontroller of some sort because the Raspberry Pi does not include an analog to digital converter. And that's actually very typical. Most small form factor single board Linux computers don't have any type of ADC on board. Generally, you'll have a separate one. And there's other things you might want to do with a microcontroller besides just that. Things that are very timing dependent. So the Raspberry Pi Pico is their new board that they've introduced, the purpose of which is to give a little bit of Raspberry Pi glamour and awesomeness. So, of course, we would like to add support to TinyGo. And naturally, one of our awesome contributors out in the world started working on it. A person named Jeff M. Hastings, who I do not actually know. But Jeff, you're doing great stuff out there. So Jeff did a bunch of work on adding the support for the Raspberry Pi Pico microcontroller. It's been, I think, a little busy lately to keep working on it, and didn't have a chance to really provide any instructions or anything. But luckily, one of our other awesome contributors in Japan decided to go and blog about this all in Japanese. So my Japanese is a bit rusty, Nihongo ma nahasemasen, but I will use the power of Google Translate to, hopefully, if I refresh, it should say something like, do you want it in English or Spanish sometimes, this time English. So this says, how to El Chica Raspberry Pi Pico with TinyGo. I'm pretty sure that's not actually translated correctly, but let's just keep digging in. So I'm going to try to follow these instructions and see if I could just flash my brand new Raspberry Pi Pico board using nothing more than this branch created by this contributor out there and this translated set of instructions from a blog post. In other words, it's the internet as usual. This is the blog post. This is the translation. This is the the branch that I was looking at. And let's see if we can get it to come up in the original Japanese. So this is the original Japanese, and this will be the English. Cool. All right. So the first thing we're going to need to do is go to our Git, and let's go over to our repo, and let's git checkout dev. So we'll go into our dev branch. And so I know that Jeff M. Hastings has his work in this feature branch called RP 2040. That's not when it's going to be finished. That's actually the name of the microcontroller chip. So that's not just like really pessimistic, like I hope I finish a Raspberry Pi by 2040 kind of thing, or when 2040 comes, it's going to stop working, or no, it's not that. It's just, so I should be able to just pull in this branch from his fork, which, if you're not sure how to do that, remember how all our pull requests have a nice little thing that shows us, well, we need to go an outside contributor for this to be easy. Oh no, QLogic is actually a member of the Tiny organization. Ken Bell, very prolific contributor, who actually we probably need to make a member of the organization. So if you remember down at the bottom of each pull request, it shows us the command line instructions. So we can cheat, right? And we can basically follow those, but just from the branch that the other person created. We don't need to only do that from a pull request. It's there in the pull request to make it easier for us to know how to do it. But that's not because it's the only way to do it. I mean, is this a good time to mention you do not need to use Git in a centralized way? There's no reason to have a Git server. You could just have your own, everyone could have their own Git. You could just mail around patches in email. That's how contributors to the Linux kernel would generally do so, is you would just email a patch to Linus, and if he liked it, then he would merge it. And if not, he would give you, some comments. So, anyway, so we can just pull this in, not this branch, but we'll git checkout -B, and we'll call it Jeff M. Hastings RP 2040, right? So we go back here and we say git checkout -b for branch, and we'll call it Jeff Hastings, or Jeff M. Hastings, and RP 2040. I believe that's, yes. Jeff M. Hastings, and it is RP 2040. Okay. So this creates our branch, right? And we want to branch off the dev branch, which is the branch that we're currently in. So that's actually a little redundant, but it's okay. Just for precision's sake, let's do it that way. And so now, remember git pull? So now, instead of git pull from Ken Bell's branch, we want to git pull from Jeff M. Hastings, or fork rather. And remember, we don't want to just git pull, we want to do git pull -- rebase so that we don't end up with an extra merge commit. And it's from Jeff M. Hastings. So this is saying git pull rebasing using this fork. And we still have to tell it which branch, which is the RP 2040 branch. So if I've done this correctly, it has just pulled on his changes and superimposed those upon the current dev branch. That should be interesting. So, if I say make, because I don't know how much stuff is in there, probably don't need to do a make, because his changes, from what I could tell from looking at his pull request, his changes primarily, if we say compare, we can take a look at that against, well, it's good enough to do it against the dev branch, or release branch rather, because that was, the release has taken place subsequently to the creation of this branch. So this way we're not showing a bunch of extra changes. So we could say he made a few important changes. He added a new makefile task to build the wrappers to the TinyGo device package from the SVD files. So the SVD files are definitions of the actual registers and hardware that are built into any particular microcontroller. It's a format that was originally created by ARM and has been sort of adopted by other chip manufacturers, loosely adopted. So we use SVD files and we take them and we run them through a processor which turns them into Go code so that we can call them from TinyGo. So he added that. He's got some linker scripts in here that are needed for the unique parts of the Raspberry Pi. He's got all the pin definitions, although not any of the I2C or SPI interfaces or anything yet. As far as I know, all it actually does right now is it does blink, which I assume it will blink on a built-in LED of some kind, hopefully. Let's go over to the instructions. So I've done the equivalent of this, and we need to make gen device RP 2040. So if we say make gen device RP 2040, that fails. Why? Because, so one of the things we're going to need to do is we have to pull in the new version of the Git subrepository, or submodule, I should say, that contains all the SVD definitions. So if we say Git submodule, update init, that will pull in all of the latest versions of the different dependencies. Quite a few of them, as there are. And so now if we go and we make device, it should work. Okay, so now we're good. So we followed that step. So we've built the device wrappers, and I don't actually need to build LLVM because LLVM was already built as a part of the make task earlier that I ran. Luckily, only the very last parts of it. So this is the sample code here. And it looks pretty simple. Not too much to it. It looks like it's just the same as our normal basic code that we use for blinking, actually. And if we go take a look at our normal blink code that's part of the TinyGo project, again under the source directory, under examples, we have a program called Blinky1. And so Blinky1 is a very rudimentary program. All it does is, like every Go program, it has a package main, imports machine, which is our hardware abstraction layer, and the time package, which is just the normal Go time package. The main function is it defines our LED, which is going to be the built-in LED on most boards have a built-in LED that you can blink. That's the hello world of things, a blinking LED. So then we're going to configure it as an output pin. Then we're going to set it low, which should be off for half a second. Then turn it on, which should be high, or high, which should be on, I should say. And then sleep for another half a second. And according to these instructions, we don't have a flashing subcommand as of yet. Is that true? Let's go look. So when we have a board definition, we have both its pin definitions, and we also have, in addition to that, a JSON file which describes how to flash it, which linker scripts to use, which flashing techniques, whether it uses the same technique as we used before, the BOSAC bootloader, whether it uses the UF2 bootloader. So, but I don't see any config JSON, or rather, I don't see any JSON definition for the Raspberry Pi. I'm not seeing it here. Maybe I need to take a look. Sometimes I noticed that I have a problem with my VS Code refreshing. I don't know why. All right, so board, Raspberry Pi Pico. But we're looking for that JSON file. So we don't want under the machine package. We actually want to go to the TinyGo targets, which is how we specify. And here it is, RP 2040, but there's no, here we go. Raspberry Pi Pico JSON. And this is a script that basically is for the linker, and it tells us that the binary format to be used is UF2. Basically, almost everything's in here to be able. He's just missing a few things, which was in fact pointed out by this kind person. So if I just take this bit of code, copy and pasting random code on the internet. Seems like a good idea. So we'll call it raspi.json just for the... And so it's not quite formatted correctly. So it inherits the Raspberry Pi Pico. That's not formatted right. It should be Raspberry Pi Pico, one word. Okay. So that's saying that this JSON file should use all of the same settings as this other JSON file here, right? And then the flash method is MSD. This is the MSD volume name, and this is the MSD firmware name. Actually, we could have just added these two things to the other JSON file, now that I look at it. Because it already has an MSD flash method in here. Well, I'm just going to follow the instructions from the blog post, from the translated Japanese blog post. That should be fine. So it's raspi.json. Okay. So we've added this flash. So we should be able to just run the TinyGo flash command like we did before. So we should be able to say TinyGo flash target Raspi, and we want to just flash the examples Blinky 1. Now, of course, we do need to actually plug in this board. So let's take a look here. We should be able to just plug in the USB. And when I do that, it seems like nothing happened. Something happened. I don't see any blinking light. Usually it blinks when it powers up. Let's see if it actually mounted a... yes, it mounted a MSD, mass storage device. And if I look at the info_uf2.txt, I see that it is in fact the UF2 bootloader 1.0 on the Raspberry Pi. So, okay, we're off to a good start. So in theory, if I run this command, let's focus. I guess I should have shown you what I was doing. Going back to the Linux here for a second. Oh, I'm just going to switch back this way here. So if we just run this command, we should be able to flash the Raspberry Pi with this new code, and let's find out what happens. No. Oh, I didn't spell Blinky 1 right. It's examples Blinky 1. Okay, it did something. Yes, it is blinking. We have made, at least I have made, my first Raspberry Pi. I'll go this far. I'll say this is the first Raspberry Pi Pico in Spain to blink. The first one in Asturias. The first one in La Pipa. Let's go. I'll keep it to that. So, yes, we're off to a good start. Obviously, there's a lot of work still to be done to make this really anything usable, but that's an incredible start. I mean, that is just amazing. The fact that I was able to go from a nice person, Jeff M. Hastings' contribution on GitHub, along with a Google translated Japanese blog post, to a blinking LED. Do we not live in a world of marvels? I think it's incredible. I mean, thank you very much. That is so cool. I really didn't know if that was going to work. I didn't have a chance to try it until now because I've been really, really busy. So, like, oh, that is so cool. Now I have to actually do some work on it. That eliminated all of my excuses about not trying to make a few contributions to add some additional features. So that's really awesome. All right. So, so there's a few outstanding loose ends of things that I didn't get to finish in some of our previous streams. And one of them that was pointed out to me from a friend was that I never actually added to the drone example the code that let you just run it from your normal computer just to take off and land. Right? That I showed that code, in my talk, but I never actually gave anyone access to that code in that repository that I created, which, if you remember, it's called like TinyGo Mini Drone, I believe. Yes, TinyGo Mini Drone. So the TinyGo Mini Drone repo, which is the repository that I created a couple of streams back to put the code in for the Parrot Mini Drone. So the Parrot Mini Drone, one of my favorite toy drones for quite a while. Here we go, Mesa. So the Mini Drone, whoops. I guess we'll just go to this other camera here. So the Mini Drone is a drone from Parrot, it's a very cool toy. You know, it's not really not something you would want to consider, you know, like a serious drone. You can get them in a lot of toy stores. So this one has got a built-in uh, little small pellet launcher and a little small arm to pick things up. I don't really haven't had a chance to play with either one of those yet, but I wanted it for these, which are Lego-sized adapter with copper conducting contacts that come directly from the battery of the drone into this little camera. So this is a first-person video camera that uses an analog signal, same one that people will use for first-person video racing, although this is not a racing drone, that's for sure. So that way we can actually see what it sees. So that's the parrot. So let's go over to the code and see if we can actually make it work, and then commit that code to the repo. Because, as was pointed out to me, it would be very nice if I would actually finish the thing I started. And I'm like, yes, okay, fair enough. I will actually do that. So, again, GVM, use Go. I'm only using 1.15 because I need to make a few fixes in order to be able to get all my Go modules files set up properly for Go 1.16. I've been meaning to do that. I haven't. This whole stream would have been me just messing around with Go package files and modules, and that just didn't sound that exciting somehow. I don't know. Maybe it would have been. So let's see. Where is this? It's Tiny Go Mini Drone? Or maybe it's just under Mini Drone. I know it's on here somewhere. Maybe it's under Tiny Go Mini Drone. I swear I have a repository. It has code. Somewhere in here. If I just list all files, yeah, sure. Tiny Drone? It's in here somewhere. Tiny Mini Drone. There we go. That was it. That was maybe not the best name. Ah, yes. So last time we were trying to get the notifications to work, but we were not successful. Reasons unknown. So let's just get stashed out of the way. And let's go back to our main branch. Git checkout main. And so let's just make sure it's up to date with whatever's in there. Yes. All right. So the thing that we were going to actually do was to add the code that was in the demonstration that I did before for my talk in FOSDEM, which is under FOSDEM 2021, yeah. And so in the demo directory here, I have all the demos I did for that talk. And one of them that's in there is this mini drone, which was a program that literally just took off and landed. So I made a bunch of changes to the actual structure, turning the mini drone into a separate package. So might have to do a little more work than I expect to make this fly, if you will. So let's go back over to, we don't want to add a new file here. We want to go back to our terminal because I didn't actually. Also, it's good to name. I use Tmux. It's good to name your tabs. So tiny drone, that way I know where it is. And we can open the code so we can actually see what we're doing. All right. So we were going to add an example that will just be like a takeoff example. Just call it takeoff. And that's going to have a main. And that main is basically going to be hopefully more or less just like this main, but possibly with a few changes to accommodate the changes that we made So I'm not using GoPLS right now because I was running in a location with no internet access and I didn't want that. Okay, so we don't need any of this positional stuff because we're not actually using the joystick. We're just going to make it fly, hopefully. And also, we made some other changes that we actually removed some of the stuff that was in here, and we pushed it into this drone, mini drone. That's actually the change that we made, is that we're not just talking directly to the drone like we were before, right? Also, one of the important things that we did was we're no longer using a direct connection to, actually I think I am here. Let's just go and take a look at the tiny flight controller and pick out pieces of it. So first of all, we need to put mini drone here for the package. Okay, no, I figured it out. That's good. It's got the Go modules file, so it was able to determine that, yes, this is where that comes from. And then we'll go back to our main. So we don't have an I2C interface or pins or a display. We do need to enable the BLE interface. So we're doing that. And then we do need to also scan for the thing we're looking for. And then I think we're doing that. Yes, we're okay. And then once we connect, we'll just display whatever. Okay, so here's where we start to diverge. So instead of saying new mini drone, we say mini drone dot new mini drone, and we pass in the device. This is kind of important because this is what matches the changes that we made for it to be a package. So it's really similar. Actually, it's very minor changes, it would appear. We start, wait 3 seconds, take off, fly for 3 seconds, then land. Let's see if that, in theory, that should work. Go read controls, and then control drone. And then the program, when it exits, it does a defer device disconnect, and that way our drone, if I quit the program by Control C or whatever, then it should, in fact, disconnect and then land. That's kind of important. So first things, let's see if we can even compile this code. So we'll just say go build. We don't need to specify a target because the target is, in fact, Linux, what we're running on here. But we do need to specify an output. So we'll just say test drone. And then it's from examples, tiny flight, or takeoff. All right, so it did build. That's good. So I guess we should try it. So I'm going to see if I can find a working battery. I used up all my batteries, as you might guess, flying the drone around while testing it. So let's plug in one of the batteries here and see if it's got any juice. Maybe. It's showing the red eyes. It's green. Okay. Also, you see I've got my camera. Let's see if the drone, yeah. Hey, we got a camera view. Cool. All right. So I should be able to run my program that I built before called Test Drone. And if the demo gods are good, then it should take off and then it should land. I guess we'll find out. Here we go. Will it work? Oh yeah. But it was kind of a rough takeoff. It knocked the camera off. But that's okay, because it did in fact fly. And I think I can just put the camera back on. And it should reconnect. Yeah. There we go. The screws are a little loose, but you can still see them. Hello! That's kind of a weird stereo type of vibe. So yeah, cool. That actually just worked the first time. I didn't even expect that myself. Wow. All too easy. All too easy. So let's take a look at the program though, because, well, first of all, let's remove the binary, because we don't want to commit that. And let's take a look at that code just to see if it's like respectably clean enough for us to, I mean, it's certainly decent. I wouldn't say it's beautiful, but it should at least sort of express the general idea of what we're trying to do here. So we can put into the README that, see the takeoff example, see the examples folder. The takeoff example should work on all platforms. So we'll make this little change here to the README, and our code is basically sufficient to at least demonstrate the basic idea. And we should see here, yes, so change to the README. So we'll get add README, and we'll also add examples takeoff, and we will get commit with a commit message saying examples, add basic, I don't want to say simple, let's just say basic takeoff landing example. That works on all supported platforms. So this should work on Linux, on Mac OS, and also, as we saw before, we can run TinyGo as the controller on a microcontroller to fly the drone around. Let's do that to make sure it's still working. So git push origin main, just to push the version back. Okay, good. All right, so let's pull out my homebrew joystick. So I didn't have a chance to work on making the joystick a little bit more professional, more solid, more transportable. This is the joystick in its current form, not its final form, its current form. And so it's got just a single analog joystick, an OLED display, 4 buttons, and then the whole thing is being controlled by an itsy bitsy NRF 52840, which is a very cool little board from Adafruit. This board uses the same Nordic semiconductor chip as the one that we just put into Gopherbot. So wait, does that mean I might be able to use Gopherbot to fly a drone? Shh, we'll do that in a future stream. Or maybe we'll just pull it out. It's like some random event. Like, hey, there's a guy with a plushie and a drone. The plushie's flying the drone. Look out, everybody. Something like that. That kind of sounds fun. All right, so if we plug in the tiny mini drone controller, it's probably running the code from before. Actually, I'm just going to hold it in my hand because it probably is, and it's just going to connect right away. That's almost for sure going to happen. If you remember, during one of our first streams, we added this little connecting message. That way we can tell when hopefully the drone is actually ready to fly. And it should be ready to fly right now. So let's switch to the drone view and go for the takeoff. that interference, or is it just too loose on the camera? The camera is a little loose. So what to do about that is there's these small screws which actually hold it in. Let's switch over to the micro camera because this is actually kind of cool. So I'm going to pop out the camera very gently, and I'm going to push these screws further in so that it doesn't come out right on takeoff, because that's what the problem is. You can see where maybe in a high-speed drone race you might want to use some glue. Maybe. So let's plug the camera back in. That's a little better, a bit more solid. And it's all still running, so we should be able to take off. And like one of these buttons was a modifier for height. Yeah, that was it. And also for the pivot. We have a few visitors today.
It's stable.
It's amazingly stable. Or is it? We'll take a little tour of the Pipa. Right? Oh, that ends our tour. That's the reason why those parts are made from plastic. And that's also one of the reasons I have multiple ones of those drones. Amazingly, it looks like the drone is still mostly intact.
Oops, sorry.
Oh, no, no worries. No worries. Thank you for bringing back my broken drone parts. That was how I met one of my neighbors. I crashed the drone in their yard, and I'd never met this person, so I went over to try to reclaim it, and I knocked on the door. She immediately said, "I think you're looking for something." I'm like, yes, I am, actually. So it was pretty funny. Luckily, she was pretty nice about it. Some people, they get really mad when you crash a drone in their yard. Other people, they have a bit of a sense of humor. Like, oh, your drone crashed somewhere in those bushes there with all the thorns. Yeah, but actually, I got the most amazing footage. It was totally worth the crash. Sometime I'll pull out that footage. Although I'm pretty sure I violated a bunch of airspace rules as well. It was supposed to go about 200 meters forward instead of going 200 meters up. So that was actually not good. All right. So yeah, we pushed the new TinyGo mini drone updates. So we've now got that takeoff example. So that should make it a little easier for anybody who would like to hopefully participate in adding some additional features to it using the TinyGo Bluetooth. There's a bunch of cool features in the drone that we haven't added yet. For example, it does flips. I know, you thought it was doing a flip before when it crashed. No, that was just a crash. No, actually there's like a flip, but you don't want to do the flip while the camera's on there. I tried that, and one time the camera stayed on, but usually not. It just goes flying off, and the camera still is not connected because it loses its power. So although it's dramatic, we don't get any good footage. And, that takes all the fun out of it. What's the point? It just looks cool, but it doesn't give you something to put onto streaming video. All right. So let's see. What did we do today? We got the TinyGo mini drone fixed up. We tested out Raspberry Pi, and we made it blink. We merged a pull request for the SPI interface for speeding up the SAM D21 interface. And wow, that was pretty cool. We got a lot of stuff going. So we have a few people in our Twitch channel. Thank you very much for cruising around, coming in, making your comments, giving us some feedback. Hopefully you're having fun. If there's anything you'd like to see, let us know, and I'll pull some items out of my hardware collection, and we can play with them together, add some new features, bring it into TinyGo, or play with some other stuff as well. What else have we got going for you here today? Oh, yes. I almost forgot. So my friend Lorenzo is here, and last time we tried to get this ESP32 board that he brought, and we couldn't even flash it with a Blink program. And, that's been bothering me ever since. Do you have one of those boards with you today? Didn't bring the board. Oh, didn't bring the board. Oh, man. I really wanted to flash that board with at least a blinking LED. I made a Raspberry Pi Blink with instructions in Japanese. I should be able to figure out the ESP32. All right. Well, we'll do that next week. Just because actually the ESP32 is a very cool board. I know I probably showed you before on the somewhere down here on the floor. I lost my Arduino Nano 33 board. So this board has an ESP32 built in. It actually has 2 microcontrollers. So the ESP32 is a really cool board. A lot of people use them, as I do myself. I usually have a couple of them spare ones around. Now, I didn't actually bring one because I thought Lorenzo would have one of those boards. Ah, man. You mean not everybody drags their entire collection of boards with them every place they go? That's why I have cases with wheels. Flight cases with wheels. That's very, very important. That's for sure. All right. So what else should we do today? Well, one thing I did want to do, actually, is I wanted to take a look at one of the things that we're working on, as I had mentioned, is coming up to add TinyML support. So TinyML is an expression not for a particular program, but for really a set of technologies for doing machine learning in tiny constrained devices. So there's a whole bunch of very cool and interesting people doing work in this space. And there's actually a symposium coming up, I believe it's next week, the TinyML Summit. So you can find out more information at tinyml.org. I'm pretty sure that quite a few people I know will be participating, either as an attendee. I know a couple of the speakers. It's definitely very interesting looking information, sort of trying to put together the different groups. There's a group of people, the Edge Impulse people who are doing a lot of cool things on ARM. There's a lot of people working with TensorFlow Lite for microcontrollers. There's actually a whole movement of people doing different sorts of things, doing different kinds of machine learning or neural networks or other statistical techniques on these tiny constrained devices. There's even a whole group of people who are doing 1-bit neural networks. So that's very interesting. So I'm not sure how much of it I'm going to be able to attend myself because of some pre-existing work-related commitments, but definitely I would recommend you check it out and then, help us add TinyML support to TinyGo. So check out tinyml.org, and it's a free event to attend. If not, just tell them Ron sent you. And no, but seriously, I believe it is free. What else have we got? Oh, so one other interesting thing that we've been working on that we haven't gotten too far yet, but we started working on an initiative to revise the TinyGo website. So the TinyGo website is getting very big. There's a lot of information on there. When it first started, it was a lot smaller. We had a lot fewer supported devices. We had fewer supported platforms. We didn't even have Windows support yet. So one of the initiatives that we have started is to revise the TinyGo website. Now, you might think that the most important parts of software are programming. And they are very, very important. But perhaps even more important is the documentation and explanations, the things that actually help people use the software. Because you could have the best software in the world, but if you have no way to get into it and exercise it, it's as if it didn't exist at all. In fact, it's worse, because you might spend an enormous amount of time trying to get it to work, but with no real directions. So we've tried real hard over the course of the TinyGo project to try to improve the documentation as we go. But we realized that we actually have gone well beyond the domain and bounds of our original documentation format. So one thing that I found out about recently is a very interesting group of documentation obsessed people. Let me see if I can find this link here for you, because it's actually quite intriguing. It's an issue, not a pull request. Started with an issue so that we could discuss this, and it's sort of been growing from there. So there's a company called Divio. I don't really know them or know anything about them, but I do know that they have done some incredible work on documentation. Not documentation of their service necessarily, but documentation about documentation. So the commenter called it the grand unified theory of documentation. So I thought this was pretty interesting enough to mention and discuss. So their particular system takes and it divides knowledge into these 4 quadrants: tutorials, two guides, explanations, and then reference materials. And I've been working on documentation and API design and API consumption and examples and tutorials and things of this sort for organizations large and small for many years. And I'm not sure I've ever seen anything quite so amazingly well thought out. I mean, calling it the grand unified theory of documentation is maybe, I haven't tried this yet myself to see if it actually works. I don't know how strong the pedagogical, I don't know how long the basic learning theories behind it are. I need a drink of water. But I can tell you that it's one of the better examples that I've seen. So we're actually looking at revising the TinyGo website around this particular system. We'd love to get your feedback, though, to see what you think. I mean, this is for you and for us. It's for all of us. So if you have a chance, definitely go to our GitHub repository for the TinyGo-site and give us your feedback on these ideas and also some of the work in progress. My colleague Ike has already started working on this with a few changes to the getting started. So take a look at those, give us your feedback, and we'd like to know because, as I said, the ability to get in and actually use it. Oh, there is one other really big announcement. Our first book about TinyGo is coming out. No, it's not my book. I'm sorry I'm running late on writing my book. Well, while I've been working on my book, someone else actually wrote an entire other book. It's awesome. So I don't have the link for it, and I don't want to just go digging through my browser history of too many things about too many technical topics to actually find just one with the word go in it, or TinyGo. That's like looking for a needle in a needle stack. But I will definitely give you some more information, both through social media and also on a future stream. Maybe we can get the author online to give us a few comments. But it looks really cool. Talks about WebAssembly and embedded devices, and it's unpacked. It's coming out, I think, next month. But we'll definitely give you more information because that's the first actual book about TinyGo. Not the last, but the first. And so that's a great accomplishment. We're really excited, and I can't wait to read it. Learn how to program this thing myself. Cool. Well, I guess that about wraps it up for today. It's been pretty awesome. We got to do a lot of fun things, explore, fix a few problems, merge some code, and hope you've all enjoyed it as much as I have. And thanks for coming, and we will see you next time here on Planet Asturias.